Section 3.10, derivatives of inverse trigonometric functions. We want to look at inverse trigonometric functions because they tell us something different than the trig functions tell us. So a trig function, you put in an angle and you get out a number. And that number represents the ratio of the sides of a triangle. In an inverse trigonometric function, you put in a number and you get out an angle. So an inverse trig function represents an angle. And so any time that we would want to know how fast an angle is changing, we would want to be able to take the derivative of that function representing the angle. And so we are going to look at the derivatives of the inverse trig functions. I encourage you to look at some of the application problems in your text so that you can see where this might be used some more. We're going to start with the inverse sine function, and this theorem here gives you the derivative of the inverse sine function, and we're going to figure out where that comes from. But first we're going to look at the graph of the sine function and the inverse sine function. So here I have a graph of a whole bunch of different things. And the first thing that I want you to know is that with the inverse sine function, this is not the same thing as sine of x to the -1 power. So I think notationally that sometimes this can be confusing because we are used to saying something like sine squared of x is the same thing as sine of x squared. But with inverse functions, that's not the case. We cannot say that the inverse sine of x is equal to sine of x to the -1. That's not true, right? This would be equal to 1 over sine of x, and 1 over sine of x is equal to cosecant x, and that's not the same as the inverse sine function. So a notation that they will use instead of this sine to the -1x, which can be confusing, is that they'll say that the inverse sine function is the arc sine function. So let's look at the graph of our sine function and our arc sine function. And the first thing that you probably notice is that our sine function, nice and wavy, goes all along the x-axis. But our arc sine function is restricted between here and here. And we do that so that this is a function. If we took this sine function, reflected it over the line y equals x to find its inverse, and we were graphing, we would get this wavy function that would go all along the y-axis. But we have to restrict it so that it will pass the vertical line test. We restrict it between this -1, negative pi over 2, and this +1 pi over 2 to make it into a function. So let's go through how we find the derivative of the sine function. Actually, before that, let's look at what actually the function sine of x to the -1 looks like. If I graph sine of x to the -1, I get this graph that looks like this green stuff, and that is not the reflection of this red sine graph over the line y equals x. An inverse would have to be the reflection of that graph over the line y equals x, and the green function doesn't do that. But what the green function is, it's sine of x to the -1 is the same as cosecant x. If I graph cosecant x, it ends up being just right on top of that. And so just so you know that the notationally this can be a little bit confusing, that the inverse sine of x is not the same as sine of x to the -1 or 1 over sine of x. So let's look at where this derivative comes from. If we have y equals the inverse sine of x, we can take the sine of both of sides of this function, and when we take the sine of both sides of that function, this sine and inverse sine, since they're inverse functions of one another, they will cancel each other out. So we'll end up with sine of y equals x. And this preserves the same relationship between x and y, it's just written differently notationally. And now we can take the derivative of this because we do know what the derivative of sine of y is when we don't know the derivative of the inverse sine. So what the derivative of sine of y is cosine of y, but we have to use implicit differentiation, so it becomes cosine of y dy dx. Ignore this triangle over here for a second. And then the derivative of x is just 1. And if I want to solve for dy dx, I get 1 over cosine of y. But we want to be able to write this derivative in terms of the variable x. And so what we're going to do is we're going to use a triangle to figure out how we can write cosine of y in terms of x. And so I use this relationship here, sine of y is equal to x, and I could even say sine of y is equal to x over 1. Well, I know that sine is opposite over hypotenuse, so sine of this angle y is represented by opposite over hypotenuse. So sine is y is equal to x over 1. Opposite has to be x. The hypotenuse is equal to 1. And if I wanted to solve for this third side of this triangle, I could use the Pythagorean theorem. Let's say we called that a. I would know that a squared plus x squared is equal to 1. And that would be then x squared is equal to 1 minus a squared. Oops, sorry. I'm trying to solve for a. A squared is equal to 1 minus x squared, and then a would be equal to the square root of 1 minus x squared. And so that length right there is 1 minus x squared. So now I come down here and I want to figure out what cosine of y is. Well, cosine of y would be adjacent over hypotenuse. Well, our adjacent is square root of 1 minus x squared over the hypotenuse, which is just 1. So cosine of y would be equal to square root of 1 minus x squared. I could write over 1, but that's still just going to be square root of 1 minus x squared. And I can substitute that in for cosine of y to get, let's write that out, to get dy dx is equal to 1 over the square root of 1 minus x squared. Now, that's the way that I do this problem. Your book does this problem differently, and I want you to look at the process that your book uses. It's a little bit different, so let's separate those. Your book uses the fact that cosine squared y plus sine squared y is equal to 1. And then they solve for cosine squared y is equal to 1 minus sine squared y. Take the square root, and when they take the square root of both sides, they get plus or minus the square root of 1 minus sine squared y. And if you look at, we know that y has to be between negative pi over 2 and pi over 2. So let's get rid of all this stuff and just look at. So we know that the y values of this inverse sine function are between negative pi over 2 and pi over 2. And if I look at, let's say I graph cosine of x, right? If I look at the cosine of that function between negative pi over 2 and pi over 2, cosine of that is positive. And so I don't need to look at the negative square root if I'm restricting the y value between negative pi over 2 and pi over 2. Right? So cosine of y is equal to the positive square root of 1 minus sine squared y. And then we can take this 1 minus sine squared y and substitute it in for cosine of y here. So I get 1 over 1 minus sine squared y but sine of y is equal to x, so I can replace sine of y with x. In either case, we get the same derivative. We get dy dx equals 1 over the square root of 1 minus x squared. We can do a similar process to find the derivative of y equals the inverse tangent of x. We rewrite this relationship as tangent of y is equal to x. We take the derivative of both sides of this with respect to x using implicit differentiation. So the derivative of tangent y is equal to secant squared y dy dx, and that's equal to 1 because the derivative of x is equal to 1. Solve for dy dx and I get 1 over secant squared y. I can use my triangle, and my triangle says that the tangent of y is opposite over adjacent. Tangent SOHCAHTOA is opposite over adjacent, so that's x over 1. And then if I solved for the hypotenuse of this triangle, I would get the square root of 1 plus x squared. Now I want to use the triangle to figure out what secant of y is. Secant of y is associated with cosine. It's 1 over cosine. And cosine is adjacent over hypotenuse. And secant is the reciprocal of the cosine. So secant is going to be hypotenuse over adjacent. So secant of y is going to be equal to square root of 1 plus x squared over 1. And then I can substitute this in for secant, and square root of 1 plus x squared is just 1 plus x squared. That's using the triangle. Your book uses the identity that secant squared y equals 1 plus tangent squared y. We know that tangent is equal to x, so we can say that tangent squared y is equal to 1 plus x squared. And so they say secant squared y is equal to 1 plus x squared, so I can replace secant squared y with 1 plus x squared. Either way, we get the derivative of tangent of, or the inverse tangent of x is 1 over 1 plus x squared. We're going to use your book, the video that comes along with your book, to figure out the derivative of inverse secant of x.
The derivative of the inverse secant. So y equals the inverse secant of x. And that's valid for all x such that the absolute value of x is greater than or equal to 1, i.e. x is greater than or equal to 1, or x is less than or equal to negative 1. So here, since y equals the inverse secant of x, x equals the secant of y. And that's valid for y from 0 to pi, where y is not equal to pi over 2. The secant is undefined at pi over 2. Using implicit differentiation, the derivative of x with respect to x is 1, and that's going to be equal to the derivative of secant y with respect to x, which is secant y times tangent y times dy dx. So dy dx is going to be equal to 1 over secant y times tangent y. So we use a trigonometric identity that says that secant squared y is equal to 1 plus tangent squared y. Solving for tangent y, that is equal to plus or minus the square root of secant squared y minus 1, but secant y is equal to x, so this is equal to plus or minus the square root of x squared minus 1. So now, talking about inverse secant, we have two cases. Case 1. If x is greater than or equal to 1, tangent of y is greater than 0, so in this case, tangent of y is equal to the positive square root of x x squared minus 1. Case 2. If x is less than or equal to negative 1, the tangent of y is negative. So in this case, the tangent of y is equal to negative square root x squared minus 1. So now in our formula for dy dx, we replace secant y with x, and we replace tangent y with the proper equation depending on whether x is greater than or equal to 1 or x is less than or equal to negative 1. We now have the derivative with respect to x of the inverse secant of x equal to 1 over x times the square root of x squared minus 1 when x is greater than or equal to 1, or negative 1 all over x times the square root of x squared minus 1 when x is less than or equal to negative 1. So using absolute value, we can write the derivative with respect to x of the inverse secant of x as 1 over the absolute value of x times the square root of x squared minus 1. This is valid for the absolute value of x greater than 1.
We could go through similar developments for the inverse cosine, inverse cotangent, inverse cosecant, and you are not responsible for being able to reproduce those derivations. We will need to be able to use these derivatives, but you don't need to do the work that went on before this. But I don't like to just give you something that's magic and say, here's these derivatives, use them, without you understanding where they're coming from. So now we're going to do several examples that combine these derivatives with some of our other rules from previous sections, and just practicing using those new rules. Again, if you are more interested in getting to the homework and practicing on your own, you could skip the examples and come back to them when you need to. There are 6 examples that we're going to do together. First one is f of x is equal to the inverse tangent of 10x, and we want to find the derivative of that. And so let's go back a slide. So inverse tangent says the derivative of the inverse tangent of x is 1 over 1 plus x squared. So the inverse tangent of something is 1 over 1 plus something squared. The derivative of the inverse tangent is that. And so if I want f prime of x, I'm going to take 1 over 1 plus that something and square it, but then I need to multiply times the derivative of that something, which is 10. The next problem is, let's do f of x equals the inverse sine of e to the negative 2x. So go back a slide. Derivative of inverse sine of something is 1 over the square root of 1 minus that something squared. And then we'll need to multiply times the derivative of the inside. So I get f prime of x equals 1 over the square root of 1 minus e to the negative 2x squared times the derivative of e to the negative 2x. We're going to have to use the chain rule again with that. The derivative of e to the negative 2x is e to the negative 2x, and then we need to multiply times the derivative of the inside of that, which is negative 2. I'm not going to do the algebra to simplify these. You can do that algebra when you are working your problems. Next example, f of t equals the inverse cosine of t, that quantity squared. So f prime of t. This time we're going to use the chain rule. The outside function is the squared, so I'm going to bring the 2 down in front, and I'm going to get 2 times the inverse cosine of t. Probably don't need those parentheses. and then I need to multiply times the derivative of the inverse cosine of t. And if you look at the derivative of the inverse functions, they are the same except they are opposite. So there's a negative in front of here. So I'm going to multiply times -1 over the square root of 1 minus t squared. The next example that we're going to do is f of u. I don't know why they make it f of u, just is asking for problems. F of u is equal to the inverse cosecant of 2u plus 1. So let's go back a slide. Inverse cosecant says we're going to take, when we take the derivative, we get -1 over the absolute value of what's inside of here times the square root of what's inside of there squared minus 1, and then we'll need to multiply times the derivative of what's inside of there. F prime of u equals -1 over the absolute value of 2u plus 1 times the square root, looks like there's a little bit of a thing left over, times the square root of 2u plus 1 squared minus 1, and then we need to multiply times the derivative of what's inside of here, so we're going to multiply by 2. And I'll leave the rest of that algebra for you. Your book's going to multiply this out and then subtract 1, and they're going to multiply the -1 times the 2, but there's not a ton of algebra with that one. F of y equals the inverse cotangent of 1 over y squared plus 1. Let's go back to that screen. Inverse cotangent is -1 over, so f prime of y equals -1 over 1 plus whatever's inside of there squared, 1 plus 1 over y squared plus 1 squared times the derivative of 1 over y squared plus 1. So I'm going to rewrite 1 over y squared plus 1 just kind of over here as y squared plus 1 to the -1 power. You could do the quotient rule if you want to. I prefer to use the chain rule. And so let's just take the derivative of this. So we get negative y squared plus 1 to the -2 times the derivative of the inside, which would be 2y. Okay, so let's look at that again. We are using this one right here, -1 over 1 plus whatever's inside of there squared. So we had to take whatever's inside of here and square it. And then we need to multiply times the derivative of what's inside of here. And so it's this derivative would be negative, bring that -1 down in front, y squared plus 1 to the -2 times the derivative of that, which would be 2y. So that's where that came from. Now, I'm going to simplify this one. It's a little bit more difficult. So this is still 1 over y squared plus 1 squared. And this is now multiplied by -2y over y squared plus 1 squared. Keep going. -1 times -2y is a positive 2y. Y squared plus 1 squared is going to be, I'm going to distribute that to both of these pieces, and I'm going to get y squared plus 1 squared. When I distribute this to this, I just get 1, because this is 1 squared over y squared plus 1 squared. Those would cancel each other out, and we'd be just left with 1. So I get a positive 2y over y squared plus 1, the quantity squared, plus 1. Last example that we're going to look at is f of w equals the cosine of the inverse sine of 2w. So we're going to have to use the chain rule a couple times on here because we have an outside, another outside, and the 2w is on the inside. And so let's do f prime of w. Start on the outside. Derivative of cosine is negative sine. Leave the inverse, or leave the inside alone, which is the inverse. So I took the derivative of the outside, left the inside alone. Now I need to multiply times the derivative of the inside. The derivative of the inside has its own outside, which is the inverse sine. So the derivative of inverse sine, if we go back a screen, derivative of inverse sine is square root, was 1 over the square root of 1 minus whatever's inside of it squared. So we did 1 over the square root of 1 minus what's inside of there, which was 2w, and we squared it. And then we need to multiply times the derivative of 2w, which is 2. Now let's do some simplification here. We have a negative sine of inverse sine. Sine of inverse sine, those are going to undo each other because those are inverse functions from each other. And so I'm going to get a sine of an inverse sine is just going to leave me with 2w. I'm going to have a negative here. That's a negative 2w times 2 is going to give you negative 4w. And in the denominator, I'm going to be left with 1 minus, and you could multiply that out if you wanted 1 minus 4w squared. That's the last example that we're going to do. And of course, our last slide, I think I should leave this off, but every time I think about that, I think, well, if I don't put it on there, someone's going to say, well, you didn't tell us to do the practice. So you need to do MML section 3.10 and then do the quiz that goes with section 3.10. As always, please make sure that you're asking questions. I'm here to help.